Hey, I'm Chubby, and I'm proud to announce that we got our paper accepted to NeurIPS 2024. As a small celebration, I wanted to record a short tutorial on the demo that visualizes our solution to a problem that exists in quite a lot of machine learning applications, especially those ones that have continuously changing training data, and to those problems that face a lot of computational constraints or low amount of computational resources, and especially those ones where you have some small delay in between observing the examples of your data and actually getting or receiving the labels from the annotation team for those samples. So how does this tutorial work? Let's get into it. So on the top, we have a three-way classification pipeline setup that has a randomly initialized model in. That's why you see all these wobbling gray bubbles. The math behind it is not super difficult. You can see that the image is a 32 by 32 matrix with the pixel intensity values, and each of the feature is practically a set of parameters that is just projecting these intensity values and summing them up into a single scalar. So we have 9 of these features, and once we have computed all the 9 features, we can compute the final class predictions, which is nothing else, again, just a linear projection. So that's how we arrive at the final prediction of the model. And our goal is going to be to maximize whenever we give some label for the network, we are going to save these labels, and we would like to optimize the parameters in such a way that they are going to always find the correct solution to the input image, or always label the image in the correct category. The next part of our pipeline is going to be the data stream. So the horizontal side, you see the memory buffer. So in the memory buffer, we have the data cards with their associated image and features. As you see that these memory cards are not updating, but they are already colored. So as soon as something gets into the memory, they will have their corresponding labels, they will have their corresponding image and their feature. And these bars that you see jumping around are going to be the corresponding scores with regards to the pending entries. In the pending entries, we're always going to see the most recent observed samples before they enter the memory buffer. So let's say that we have small delays in between observing these samples and before they can actually reach the memory. And you see that there's a slight delay in between the top card on the top and in the bottom of the pending entries. And these bars are jumping around because at each time step, we are just computing their similarity for each of those to the ones in the memory buffer. So later on, we can always just compare whether a new feature or a new image was similar to one of the memory samples or not. Let's go back to the simple case when we have 0 delay in between the observation, the labels, and the memory buffer. So it's a very, very simplistic classification problem that we are going to use for the visualization. And I'd like to invite one of my biggest helpers throughout the project, Ducky. And I'd like to use Ducky to create my class 2 objective. And now we are going to actually fine-tune the network using these two classes. And manually, we can just click on the button update model. And we see that by each update, we are going to update this theta parameter, which represents all the ways that project into the feature vectors and that make the final classifications. And in real time, you can always just try out whether the classifier works correctly or not correctly. And yeah, this is very classical training scenario when you have a static data set and you just train something offline and you deploy it somewhere in the test set. Now, the biggest problem with this is that oftentimes there's slight smaller or larger distribution shifts of your data when you are deploying a network. And it's a well-known issue with the current AI models that as soon as you change the test distribution of data a slight bit from the training distribution, there's no guarantee that your accuracy or your performance is going to generalize to the new distribution as well. So online learning is something that is inherently tied towards temporal evolution of this distribution. What that really means in fancy words is that over time, if your distribution changes, for example, the appearance or the rotation of Ducky is going to be different over time, then we can just like always fit the network to train on the most recent appearance of our class. And, like we see that, it's perfect, like the accuracy is going to be perfect on this new representation. But at the same time, the model started to forget about the most important class, me. So in order to fix this, now we are forced to train and add new samples again to the memory. And now, of course, the online learning works. Yay, our performance is a 100% because all the data that we are currently seeing is just class 1. And if I bring back Ducky, there's some likelihood that, like the parameters are still generalizing to previous examples from the past. But most likely it is going to be the case that it is just using the most recent samples as the most accurate representations. So to fix this in online learning, what usually people do is that they train on the newest images. So for example, here I can choose to always update on my first 2 images in the memory buffer, and whatever comes after these guys are always going to be discarded. So my representation is always going to be fine-tuned on the most recent images, because we don't really care about what has come in the past. We always care about overfitting on the most recent distribution. And to some extent it works quite well. For example, if I bring my second companion, Red Robin, and add her as class 3, then we can try to see what happens. And in this situation, there's some generalization going on, but the problem is going to be that as soon as a new class starts to dominate the entire setting, and for example, our distribution is not well balanced, so all the classes are coming in huge batches and they are not evenly distributed, they are not an IID distribution, then the network is going to face again some difficulty. So this is what online learning is mostly concerned about, like how to fit the most recent distribution as much as possible. But it doesn't really concern about like, what happens if you bring something back from the past? Like, do we perform well? Do we perform badly? Yeah, we don't really care. We always just care about the present. But continual learning is actually addressing these sort of issues on the other hand. Continual learning is concerned about the performance on past samples and past accuracies. So what we'd like to achieve is that, you have a model that can be trained over time. Instead of retraining it from scratch on all your current data that you have aggregated all over the time, you just want to allow your model to use that information to learn faster newer classes and retain some of that information, such that when you bring back some old examples from the memory, it should still perform quite well on them. So when your model just like forgets about the past example, let's say I just keep fine-tuning on myself and Red Robin, then probably after a few iterations, we are just going to see that the Ducky class has been almost ignored. So the network has forgotten what Ducky was looking like. Now for this reason, we can do a very simple trick, which was introduced mostly in reinforcement learning and got adapted by my dear lab mate, or ex-lab mate, Arslan, which is memory replay. It's a very simple technique, very simple continual learning technique, where you are just trying to find the newest sample. You're trying to fit on the newest sample of your distribution, and you just select some memory samples from the past to actually retain some of that information, as long as you actually have, like a sufficiently large memory buffer. Let's try to increase it. And, as soon as we have some more memory samples, we are going to be able to store some representative classes for each of our representative images for each of our classes. And with this idea, we can say that, as long as we keep using one of the newest and then some of the random memory samples, we are going to keep our model updated and focus on the most recent tasks at hand, or the most recent state of the distribution. But it is also going to be forced to retain some memory or retain some performance on past examples. A next complication that is exposed or that is present in most of our practical examples or practical problems is the label delay. The problem of label delay actually arises as soon as you have any sort of like irreducible time between receiving your labels and allowing your model to overfit on the current distribution. So whatever you see here, for example, if I have the red robin, as soon as I press number 3 or click on the add category 3, you see that, like the training data immediately updated and our model could be overfitted on it, which is great. And like all the papers just assume that there's like zero delay in between receiving the label and seeing the newest example. But in practice, and this is what our paper is really about, is about label delay. So what we see here is that as soon as you have some non-negligible difference between observing the input images and training your model, then you are going to face this issue that even though you are trying to always like overfit on the most recent sample to keep up to date with the distribution, if your distribution started to shift, for example, instead of the new duck is, you could just like overfit on this duck, but you are going to see some newer versions of it, then even though that you believe that the best example to train your model on is going to be the most recent sample in your memory buffer, probably that distribution is going to be outdated. The bigger this delay is going to be, let's say we try to reduce the FPS, you can say that, oh, suddenly everything became laggy. And now, if this is my most recent distribution, then you can see that, oh, training actually on the newest samples is not going to give you a lot. So it's not going to help you a lot. Because instead of actually being able to train on the most recent and most representative samples, you are just going to train on something that's old, quite outdated with your dataset. That just increases back, so we reduce the amount of trippiness. So what we are trying to do here in this paper is the following. We use the importance weighted memory sampling, which means that we are going to compute this importance score for each of our memory samples. So you see that our current image, even though it doesn't have any labels, any ground truth appended to it, we can already compute the features when we are trying to make the predictions. And when we are trying to rehearse the relevant samples from our memory distribution or from our memory buffer, then we can always just like look at those samples that are actually relevant to what we are going to observe in the future. And the more recent the samples are going to be in our memory, the better the alignment is going to be. And even though I don't know what is going to be the label for this sample, as soon as I receive the correct label for this, my network is going to be very prepared. And, instead of like spending loads of compute to try to do something smart in the back and just like use self-supervised learning, use any sort of like unsupervised techniques or pseudo labeling or anything like that, we are just using this indexing technique. And it comes very cheaply because just imagine a production system. You need to flag if any of these images are explicit. In those cases, for example, you are always making predictions of each of your images in your current distribution. So you have these features pre-computed. And as soon as you actually receive any label for these images, you can just save those features alongside with the original image. So you can use it as an indexing technique. And it comes very cheaply because the only thing that you need to do is to compare these 9 numbers against each other and just tell me how far is this example from my current distribution in the memory. And instead of retraining always on the newest and some random sample, we can just fine tune on the most relevant samples from our training distribution and some random sample to just retain, like some sort of regularization for the model. So this technique is very cheap. It comes at almost zero cost. Apart from this memory computation or memory indexing, there's not so much of overhead. And like the lower dimensional features you have, the more cheap it is going to be. So there's a really nice trade-off handle on the entire process. It works generally with all kinds of backbones, so you are not restricted to linear models. Here in this online example, we can replace the linear backbone with a ResNet, with some convolutional nets, or with some mobile nets. And they all work just fine. All you need to do is just like store the corresponding features to each of your input samples. And yeah, there you go. Well, actually, there's one cool feature that I wanted to share as well. So if you are interested in reproducing all of these results, then you are lucky, because you can just save the save stream button, and this will allow you to save a zip file. And in this zip file, you are going to have all your images that you have recorded sequentially indexed with all their corresponding labels, which is great because if you want to reproduce the results, you just reload the page or open a new page, or you can also send it to one of your friends, set the configs accordingly to your own experimental requirements, and once you have set it, then you can just replay the entire stream, what you have just observed. So here now we are going to go through the entire training data and ideally come up with the exact same results what we have gotten in the previous training. But obviously here throughout, if you change anything during the training, it's not going to look exactly the same. If you want to have always the same results, then throughout your recording, you should always keep the configs the same. More importantly, these results look nice and like they look great, but if you actually are interested in the numbers, you should press the tilde button that is going to pull up this side panel, where you can check out all your accuracies and all the metrics that you could trace throughout the entire training. And ideally, this is also going to shift the paradigm of always just using prefixed benchmarks with millions and millions of samples and very expensive experimental setups. So you don't need to actually take ages to set up a new experiment where you are just interested in learning what happens if you poison your dataset. Let's say Ducky here is recording himself as category 1 sample, and I'm just curious how quickly my model is going to overfit on Ducky with the wrong class label, and what happens if we switch spaces and, for example, I train myself as class 2. I'm just interested in all of these results, and you don't need to write new code. You don't need to do anything. You can practically just like press buttons and explore all the effects and benefits of using these techniques in online continual learning. So yeah, without further ado, I would like to ask you to try this demo out. And if you do have any questions, please do reach out to us. Check out the paper where we have actually a really massive evaluation on all different like million large data set, and we show really interesting results and really interesting scores. And yeah, hopefully we are going to see each other soon at NeurIPS. I'm going to present this work on Friday at the poster session, so please do come and say hi. Thank you.